So this is mine and Harrison's NAS reaction overview. NAS is also known as Nucleophilic Aromatic Substitution. The significance of this is that NAS is used to substitute one substituent on an aromatic ring for an alcohol. So for example, 1-chloro-2-nitrobenzene could be reacted with a hydroxide to form 2-nitrophenol, and that product, or this product, is just the same as this, but the chlorine has been replaced with the OH group, making it an alcohol. This process is pretty important for some pharmaceutical drugs. It's used in some antimicrobial drugs. I don't really know the name of any of them, but yeah. Another example of that use is NAS being used in the synthesis of heterocyclic atrop isomers via non-atrop isomeric intermediates. Atrop isomerism is a type of stereoisomer that is characterized by a hindered rotation about a single bond. Basically what that means is there's some bond in the middle of the atom that, due to steric hindrances and whatnot, it can't really rotate, and that means when it reacts with, or I should say interacts with, certain receptors in the body or bacteria or whatnot, it only fits in one way, so you're not really worrying about like enantiomers or anything like that. But this is very important for pharmaceuticals, and that will lead to the formation of new medicines that, like I said, are shaped to have those very specific interactions. This is all from PubMed. The source is right here if you want to click on it. I don't know if you can, but that's the name of the paper. And then there's three main types of NAS. The first of these is Meisenheimer, which is characterized by deactivating groups on an aromatic ring, like NO2, as well as a halogen. So a good thing for Meisenheimer would be like dinitro bromobenzene, whatever the numbers would be. Which Harry will get into that more when we're going over the mechanisms, but the positions do matter, like ortho, para, meta, but we'll get into that later. And essentially, this reaction is just whatever your starting material is reacted with hydroxide. It's like sodium hydroxide or something like that. And it will replace the halogen with an OH. The second type of NAS is alkali fusion. This is characterized by an SO3H group on an aromatic ring. These are all going to be aromatic rings, but it's carried out with two steps. The first step uses sodium hydroxide and heat. This heat is very high. I don't remember what it actually is, but it is a very high temperature. And then it's followed up with H3O plus normally, which is just a quenching step. Yeah, not a whole lot is super clear about alkali fusion so far, but yeah. The last reaction type is benzene, and this gets its name from the intermediate it forms. So, whereas benzene normally has those three double bonds in its aromatic system, like this is how you see it drawn, benzene has two of those double bonds, and in the third position it's a triple bond. This is very reactive. It's super high energy, and this intermediate is formed by taking a ring that has, say, a chlorine on it, or I guess just any halogen, and you react it with hydroxide, and that would form your benzene intermediate, and you follow that up with water, which would add on the hydroxide in either the position of the chlorine or in the position next to it. That is because wherever the double or the triple bond is forming to make the benzene intermediate, the OH will add on either side of that triple bond, meaning you're going to get 50-50 of two products, because it's equally likely that it adds on either side. Okay, so now we're going to move on to the mechanisms, and I'm going to let Harrison handle that.
Alright, so going off what AB said, we're going to start with the Meisenheimer because there is 3 different types of reactions within the NAS kind of area. The Meisenheimer, it doesn't react with meta. It just has no reaction. So it reacts ortho and it reacts in the para positions. The ortho position ends up usually having about 2 intermediates, and we're going to go through those. So to start with, you can, like you have this nucleophilic alcohol right here, and the lone pair on those, which right there is kind of imaginary, goes and attacks this carbon right here. And since it attacks that carbon, it kicks this double bond right here onto the double bond, or not the double bond, I'm sorry, the carbon right here, and that creates the first intermediate right here, and it has an electron pair on it, creating that negative charge. Because in nucleophilic aromatic substitution, the ring is usually an electrophile. It's always an electrophile. But in the first step of the intermediate, you're going to have these lone pair right here create a double bond with that nitrogen and the carbon in the ring, which kicks that oxide or that carbonyl, this right here in that little double bond, kicks that up to make another electron pair and makes a negative charge. And the next step of that one, you're gonna have an imaginary lone pair right here. It's gonna kick back down because you want to kick this halogen off. So in our scenario, just X, which it could be chlorine, bromine, but a lone pair goes back here, creates that double bond to the oxygen and nitrogen, which kicks the double bond from the nitrogen and carbon back into the ring, which then forces this halogen out and creates that as, for example, a Br negative. And then that kind of gets you the para product, or not the para, the ortho product. In the para product, kind of the same general idea for the start. This electron pair will attach where that halogen is on the same carbon, and then this will kick off onto that carbon right there and create our first intermediate with the electron pair. And then it just resonates throughout the structure. So you go here, create a double bond, which kicks this double bond and makes a lone pair on this carbon connecting to the nitrogen, as you see in this step and right there. And you can do it again by putting this onto the double bond to a nitrogen and carbon, which would, again, like in this step up here, would kick this double bond to the oxygen and nitrogen over to the oxygen, creating a negative charge. And to get back over pretty much, I did switch the sides up a little bit, but you can get the lone pair right here, which attaches to the nitrogen, and it kicks the lone pair, kicks back there, creates a double bond, and which kicks this bond right here back into the ring, which kicks this bond in the ring back over here, and then it kicks the halogen off again, repeated process, and then it gets you that para product. Now, alkali fusion was a tricky one because at first we were kind of figuring out what's the mechanism to this, because we don't remember really going through the mechanism very much, and that's because the mechanism is unknown. Some of the reasons are, it just requires super high temps. One thing we do know about it, though, is activating groups on the ring speed up the reaction. And also, since we didn't really have a mechanism, I just wanted to put the major product here and kind of show what it does. There's a SO3H on there, and pretty much, in simple terms, it just swaps an alcohol with it. Simple as that. This kind of puts it on there. This quenches it to create the actual hydrogen. And yeah. And then the next reaction is the benzene. And I think this one's a super unique one because it gets you the triple bond right here, which no other reaction necessarily does. This one's different. It does, instead of attaching here on this carbon, it actually goes and deprotonates. It just takes this hydrogen off and creates an H2O, and then the bond from the hydrogen goes into the ring, creating that triple bond, which would be our intermediate in this step, and some just kicks the halogen right off, which creates the Cl negative. So in this step, it's 50-50 in the product, because as you see here, you can either go here or here. It's the exact same. We don't really know which one. So we'll always have two products, and it's going to be 50-50. The lone pair on this electronegative oxygen is going to attack the partial positive carbon in that spot right there. And it pretty much, if you're looking at it, almost uses that double bond or that triple bond right there, and one of those bonds creates. So it, in this step right here, you still have two bonds right there, but one of the bonds ends up creating that alcohol. And same in this step, that bond kind of uses it for the alcohol right there. And yeah, the oxygen just attacks, and it creates a 50-50 product. Can attach either way. And yeah, those are the three mechanisms of NAS.